about gravity. You've all heard of the good old story. The apple fell down from the tree, hit Newton on the head, and he discovered gravity. But Newton only gave us a formula that tells us the strength of gravity, but not how it actually exerts its pull. Newton was fully aware of this problem's difficulty that he left it for us to solve for him. And that's when Albert Einstein proposed his theory of general relativity. Well, you may think gravity is just a force that pulls two objects together. How simple is that? But according to Einstein, you're very wrong. Gravity is the distortion of space-time.
So, what is space-time?
Space-time is a four-dimensional Hausdorff differential manifold on which a metric tensor is imposed to solve the Einstein field equations, and that metric tensor gives rise to geodesics and objects that are not experiencing any other force moving along the geodesics described by the metric.
Before general relativity, Albert Einstein proposed that space and time are inseparable. You cannot move through space without moving through time, as it takes time to move. And you cannot measure the passage of time without reference to things moving through space. Space and time are interwoven into the same piece of fabric, a single continuum called space-time. General relativity is basically about how matter interacts with this fabric of space-time. Space-time tells matter how to move, and matter tells space-time how to curve.
And the Einstein field equations basically describe gravity as a result of space-time being curved by mass and energy, which specifies the space-time geometry.
Whenever there is mass, the mass distorts space-time. This produces the same effect as putting a heavy sphere in the middle of the trampoline. The bigger the mass, the bigger the warp. The smaller the mass, the smaller the warp.
Now, imagine if we roll a marble around the dent that the ball creates. The marble will spiral around the body, pulling it and orbiting the same way that the gravity of a planet pulls at rocks in space. In our demonstration, the marbles flow inwards because friction exists between the fabric and the marble itself. However, in space, there is no air resistance and virtually no force acting on the matter in orbit, and so the planets would be swirling inwards.
Right now, you probably can't visualize space-time, and that is perfectly alright because space-time is a fourth-dimensional model, and we are only three-dimensional creatures capable of viewing two-dimensional objects and imagining 3D stuff. And here is how the real one looks more like. Alright, now we have a basic understanding of general relativity. But all this fabric and fourth dimension, how do you prove this is true? Consider this hypothetical situation. You're an observer standing on Earth trying to look at a star. The Earth, the Moon, the Sun, and the star are perfectly aligned. You'd probably think like Newton or other scientists at the time that the observer wouldn't be able to see the star because light rays travel in straight lines, and the Moon blocks the sunlight enough for stars to be seen near the Sun. On May 29, 1919, this very phenomenon happened, and Einstein's four-year-old theory of general relativity was put to its first test during a total solar eclipse. And on the day, the star cluster called the Hyades, passing just behind the Sun, could be observed but appeared displaced. This very phenomenon, known as gravitational lensing, verified the theory of general relativity because it proved that the path of the light is bent and space is not flat. Light still chooses to travel the shortest distance from one point to another, but on a curved plane. Imagine you and your lover standing on two separate points of the equator, with both of you facing the north. You thought you'd never meet each other again, but once you get to the North Pole, your lover is right in front of you. This isn't just love from fairy tales, this is physics. The gravitational field of a massive object with massive mass will extend far into space, and the path of the light rays passing close to that object through its gravitational field will be bent instead of what we predicted as straight.
The Einstein ring forms when a distant light source, like a galaxy or a star, a spherical gravitational source, which could be a spherical galaxy cluster, and the observer line up precisely. Light, traveling in a straight line, is bent equally in all directions by the presence of this symmetrical, massive body which causes huge distortion of space-time. The light is therefore deflected to form a ring instead of clear images, coming to the observer from all directions around the lens. This phenomenon was discovered in 1988, almost 80 years after Einstein's prediction, and this Einstein ring really secured his proposal of general relativity. This beautiful ring-like image was recently captured by the James Webb Space Telescope, where a distant galaxy has been magnified and wrapped into a perfect ring by a spherical foreground galaxy cluster. But when a gravitation source is not a sphere, but an ellipsoid, 4 images instead of a ring are formed.
An image called the Einstein cross was discovered in 1985, which is formed when the light from the quasar, an extremely luminous galactic nucleus powered by a supermassive black hole, is bent by an ellipsoid galaxy called a Hawksbill lens. Before reaching the observer, this galaxy, ellipsoid in shape, acts as a gravitational lens and distorts space-time, and the light from the quasar bends when traveling back to Earth. And we perceive this light traveling from 4 directions, creating 4 separate images of the same object, forming a nearly perfect cross, and the center of this image is the foreground galaxy.
The power of gravitational lensing is astronomical. It enables scientists to detect the existence of originally unobservable but making up 85% of the universe's mass, dark matter, and to study the most distant galaxies and the supermassive black holes far, far away from us.
Newton left an unsolved mystery to us, and it was Einstein who provided the answer to his question, proved conventions wrong, and discovered that gravity is the curvature of space-time. The universe knows no boundaries, and there is always endless space for us to explore, to engage, to learn, and to enjoy. Peace out and bye-bye.